Fringe width concept is very important here. Fringe width denoted by beta. On the screen there are alternate bright and dark bands. Suppose this is bright band, then there is a dark band, and these bands are alternately produced. Bright, dark, bright, dark. Suppose bright, this is dark, then again dark, then next one will be bright. Here this is bright, bright, dark, then dark, bright, and so on. Central is always bright. So what is the fringe width? The distance between two successive bright band or two successive dark bands. The distance between two successive bright bands or two successive dark bands, or it is the distance between successive maxima or successive minima. And that bandwidth beta is lambda capital D upon small d. Very important formula. Lambda is the wavelength of the light. Capital D is the distance of the source, distance of the screen from the slit. Small d is the distance between the coherent sources. So here, as this capital D and small d are constant, then this fringe width beta is directly proportional to lambda wavelength. Fringe width beta is directly proportional to wavelength. If wavelength is more, fringe width will be more. We know for red color wavelength is more. For violet wavelength is less. As wavelength is less for the violet, wavelength increases from violet to red, we know. As wavelength is less for violet, fringe width will be also less for the violet color. Wavelength is more for the red, fringe width will be also more for the red. This is the conclusion from this. As this capital D and small d are constant, fringe width is directly proportional to wavelength. You should know this relation to solve the MCQs. Then we see some important points related with this fringe width. As beta is equal to lambda capital D upon small d, and as we also know, this beta is directly proportional to lambda. Fringe width is directly proportional to lambda. Then first important point is, if Young's double slit experiment apparatus is immersed in liquid, some theoretical MCQs are asked on this article. If Young's double slit experiment apparatus is immersed in liquid of refractive index mu, refractive index of that liquid is mu. From air to liquid, we know refractive index, wavelength decreases. From air to denser, wavelength decreases. So lambda decreases, wavelength decreases mu times. And as beta is directly proportional to lambda, hence fringe width beta also decreases mu times. This is one important concept, as beta is directly proportional to lambda. And if Young's double slit experiment apparatus is immersed in a liquid of refractive index mu, as light goes from rarer to denser medium, wavelength decreases, so lambda decreases the mu times, that is the refractive index times, and as beta is directly proportional to lambda, hence beta, that is the fringe width, decreases mu times. Second important conclusion here is, in Young's double slit experiment we use the monochromatic light, that is the light of single wavelength. We use the monochromatic light of the single wavelength. But if we use the white light, if white light is used in Young's double slit experiment, white light consists of 7 different colors from violet to red. It is not monochromatic. It consists of 7 colors having the different 7 wavelengths. If white light is used in place of monochromatic light, colored fringes are obtained on the screen. Instead of bright and dark fringes, colored fringes are obtained on screen, because it consists of 7 colors. Colored fringes are obtained on screen with red fringes of larger size. Red fringes of larger size than violet fringes. Because wavelength of the red color is greater than wavelength for the violet color. If white light is used in place of monochromatic light, we get the colored fringes on the screen with red fringes of the larger size than the violet, because a wavelength of red fringe is greater than the wavelength of violet fringe, but center of the fringe is still white, because a path difference is 0 there for all colors. Center of fringe will be still bright for the white light. Center fringe is bright, but the other fringes are colored. Then one important point, we find the angular width of the fringe. We know fringe width. Now we find angular width of the fringe in Young's double slit experiment. The formula is important for the numericals. Angular width of the fringe in terms of angle, angular width of fringe. Angular width of fringe. Firstly, we find angular position of nth bright fringe. Then we find angular position of n plus 1th bright fringe. And by taking the difference, we get angular width of the fringe. Firstly, we find angular position of nth bright fringe. Angular position of nth bright fringe. We denote it as theta n. For the nth bright fringe, we write it as theta n. If theta n is small, then that tan theta n, we write it only as theta n. And from that figure, theta n is yn upon d. Theta we know, y upon d. For the nth bright fringe, we write that distance as yn. Theta n is yn upon d. But yn we know, it is n lambda capital D upon small d divided by capital D. This capital D get cancelled and we get that theta n as n into lambda upon small d. This equation gives angular position of nth bright fringe. For next bright fringe, suppose this is 5th, next will be 6th. If it is nth, next will be n plus 1th. So for next, that is n plus 1th bright fringe, instead of theta n, we write it as theta n plus 1. Angular position will be, for the nth bright fringe, angular position is theta n. For next n plus 1th bright fringe, angular position is theta n plus 1. Similar to this equation, that theta n plus 1 is yn plus 1 upon d. And similar to this equation, instead of n, we write here as n plus 1 lambda capital D upon d divided by d, and we get the equation theta n plus 1 as dd get cancelled, n plus 1 into lambda divided by small d, equation 2, n plus 1 lambda upon small d. Now we find the angular fringe width, that is the difference between these two angles. This is for the nth bright fringe, this is for the next n plus 1th bright fringe. Angular fringe width is the difference between these two angles. So angular fringe width is, see here, angular fringe width, we call it as theta, and that is theta n plus 1 minus theta n. Simply take subtraction of these two. Theta n plus 1 we know. What is that theta n plus 1? That is n plus 1 lambda upon d. What is theta n? N lambda upon d. Sorry, here that d is small d. N plus 1 lambda upon d. This is n lambda upon d, and this angular fringe width theta will be then n lambda upon d plus lambda upon d minus n lambda upon d. This plus minus get cancelled, and we get the expression for the angular fringe width as a lambda upon d. Lambda upon d. This is the angular fringe width. Now we know this theta is angular fringe width. But we know the fringe width beta is lambda capital D upon small d. Suppose this is equation 1, say, angular fringe width, and our fringe width beta is lambda capital D upon small d. From this equation, lambda upon d is beta upon capital D. Beta upon capital D. This lambda upon D, we get it as beta upon capital D. So angular fringe width theta is equal to lambda upon small d, or that is also equal to beta upon capital D. From this expression it is clear that this angular fringe width does not depend on n, that is the order of fringe, whether it is first bright or second bright. It is independent of n, that is the order of fringe. Hence, angular width of all fringes are same. Angular width of all fringes are same. So this is the some important formulae or synopsis related with interference and Young's double slit experiment. This synopsis is very important. If you read it carefully, you can easily solve the theoretical multiple choice questions, also the numericals based on interference and this Young's double slit experiment. We stop here. Thank you.